Hi, this is a description of some of the details of how to do the Chem 104 data treatment lab, particularly going over functions and calculations in Excel. When you download the file from Canvas, you should have data already in the file. So we're just going to do calculations based off these 8 values that should be, or that we assume are going to be, should be equal to each other. So first thing, put in your name. Name, that looks good. And then it seems like the first thing we should calculate is deviation, but to calculate the deviation is equal to the average value minus one individual measurement in the list. So really first we need the average, and there's a good function in Excel, average. You type it and then type an open parentheses, select the data that you want average, close parentheses, and we've got the average. And this is an auto-graded lab, and so I did that correctly, and I get 5 points out of 5. This little green triangle, sometimes that'll show up if you have an error in the calculation. In this case, what's going on is this Excel file has some locked cells, so cells you can't change, like these over here that do the grading, and this is indicating this is an unlocked cell, which means we can type things in and do the calculation. So in this case, that is not an error. Now to calculate deviation, we're going to take that average value and subtract the one of the particular values from the list, and that's how you do that. Instead of having to retype that formula in all these cells, one thing you can do is you can take this, and when you get this little black cross without the arrows on the end, you can click and drag down, and this will copy this. Now right now we do have a problem here. This does not look correct. These don't look like the deviations. They're the actual entries. And what's the problem there? Well, if we look up, this is what I was copying. You can see is B17 minus B5. And so B17 is here, B5 is here. That's how we get that deviation. If we go down when we copied it down one row, it increased the row number for both B17 and B5. And now it's B18 and B6. Now, B6 is correct. That's the next entry in the list, the next deviation I want to calculate, but B17 isn't here, it's here. And so that's not we're not taking the average minus the second entry in the list. So what you can do is, if you put a $sign in front of either a row designation or a column designation, that will sort of fix that. And here we're just copying down in the same column and down rows, and so all I need to specify is that never change the row from 17 to 18 and 19 as we go down. If I was potentially going to copy also left and right, you could also put a $sign here. I'm not doing that in this case, but it won't change. You can sort of think of this $B, $17. That means we're always going to be taking the value from this particular cell. So I'm going to do that, and now I can't copy this new entry down, and we get the deviation. So that worked good. Deviation squared, we're just taking this value and squaring it. You can multiply it by itself, so like times C5, that's one way to do it. You can also use a caret, which creates a power, so caret 2, that'll do it. And here we don't have to use any $signs to specify, because we're only using this cell right here, and when we go to the next entry, we want to go down one to C6 and C7. So this we can just copy all the way down. There we got it. One weird thing is, you can see we got lots of different numbers of sig figs. Up here, this says that we have a numbers here. We do have, we have 3 sig figs or 1 sig fig in some cases. So we definitely have like way too many significant figures here. So we can sort of make these a little smaller. The trouble is this isn't quite, when we do the squares, we don't get quite the right number of sig figs. Like here has 1, this has 1, that seems right. This has 3, right now this has 4, so I might want to do that once more. You don't have to go through and do this. This has 2, therefore I want this one to have 2 also. Whoops, there we are. So but this, when you have a number here, you can use these 2 little buttons to increase and decrease the number of decimals shown. And usually we won't do that. You'll do something more like this, where there'll be a little cell that says what's the number of sig figs, and so that's for this average, and you should answer that on your own. Over here we want to calculate the median. That's the middle entry in a list of values, and if it's an odd number of entries in the list, then you can take the value where we have equal number of entries above and below. If it's an even list, then we take the average of the middle 2. So there is a nice function in Excel, median, and we can just select this data and calculate it like that. And so median is nice. One way to calculate the range, so the range is the largest value of the list minus the smallest, and we can use another function. There's a function called max. Oops. And max is going to, then we take max and open parentheses, and we select all this data, it's going to find the largest value. If I put that in here, you can see it's looked through and found that 6.8 is the largest value. But here I want the difference between the max, the largest value, and the smallest value, and min is the function that finds the smallest value in a list. Like that. All right, average deviation. It might seem like what you could do is just take the average of the deviations, but I don't get any points for that, and it's equal to 0. And the problem is that the average deviation is the average of the absolute values of the deviation. So here we have some positive, some negative values, and this is the average of the absolute values. So there's a couple ways to do that. One way, you could just go over here and have you could calculate or enter in another, and just there's another function is ABS for absolute, and you take the absolute value of this, enter, and then you could just enter all those. So now we have the absolute values of those entries, and the average deviation is the average of these. So that's one way to do it. I just wanted to show you a couple of things there. It turns out a simpler way to do it is to use a function called avdev, and that will, here you don't do anything, you don't use the deviations, but you go through and you select the original data, and it's going to calculate the average deviation for this list of data, and that gives the same value and works. Anytime you see something that says percent relative for these values, what you want to do is, it's always, you're going to divide the original quantity here, average deviation, by the average and multiply by 100. The advantage of relative or percent relative average or deviation or percent relative anything is that it compares a particular value to the size of the quantity it's derived from. So the problem is like 0.5 grams, a 0.5 gram deviation or average deviation out of 2.5 grams is kind of a lot. That's like 20%. But a 0.5 gram deviation out of 100 is only 0.5%. So if I say my average deviation was 0.5 grams, that tells you something, but it is also helpful to know, how big is that deviation compared to the list of data itself. And so then saying it's 20% or 0.5% is helpful. So as I said, always percent relative quantities in these statistical things. You say equals, and then you're going to take the original quantity here, the average deviation, divide by the average, and multiply by 100 to make it a percentage. Standard deviation, you can look up the formula in the lab manual. It's a little hard to describe verbally, but there are two different formulas. One when you have a number of entries in the list less than 10, and one when you have it when it is more than 10. Here we have less than 10 in Excel. The way we do that is with something called stdev. This will be for where the numerator is n, not n minus 1, or n is the number of entries, and we just can do that. If you want to use the other type of standard deviation, that's something called the population standard deviation, and here we'd put in standard deviation, we'd put a p there, and if we put that, we see we get a little bit different value, don't get points there, and so I'm going to take out that p. Remember, standard deviation is pretty easy to do. Variance is the standard deviation squared. 90% confidence limit. So this is sort of based off of sort of lots of studies of the statistics of random errors in physical measurements. There's a table that we have in your lab manual. In my lab manual, it's page 35, and it shows a table that says values of student T for calculating confidence limits at 90%. And the confidence limit formula says that you take the uncertainty from the average is the t-value times the standard deviation divided by the square root of the number of entries. So you have to take a value from this t-value table, and it's based on how many samples you have. And we have 8 data points here, and so the value of t for 8 data points is 1.895. So I'm going to take 1.895 times the standard deviation, and then I'm going to divide by the square root of the number of entries on our list, and that's 8. And there we go. So this means that based off of if our experiment follows the statistics that the t-values were calculated with, there's a 90% confidence that the true value falls within the average plus 0.049 and minus 0.049. So that gives us a little range that we should be 90% confident the true value falls in that area. Finally, Q-tests. Q-tests are done if you have an entry particularly if you have outliers, values that are sort of much higher than the rest of the data or much lower. And what you do is calculate a Q value, which we'll do here in a second. And if the Q value is larger than the entries on this second table I have on page 35, it says values of Q for rejection of data at 90% confidence. So if our value of Q is larger than, for 8 values, we can see that the value is 0.47. If our value of Q is larger than 0.47, we can say that outlier, the very high or very low value, we can say there's a with 90% confidence, we can say that's somehow an unrepresentative outlier and disregard it. So we have to calculate the Q value, and the Q value is calculated. You can in your lab manual you should see it's equal to the absolute value of the number that we're going to question, and we always want to question the highest value in the list and the lowest value in the list. Those are the ones that could be outliers. So I'm going to take the max of this list, and then you take the difference between the max, the largest value, and the next closest value. And the idea is that if that value is kind of big, then it's more likely this is an outlier. That will increase the Q value, and we'll get a Q value more likely rejected. So we take the difference between the largest value and the next to largest. There is a function that's helpful for that, and it's called large. And what this does is you specify a set of data, like I did here, whoops, and then put a comma, and then the next value is you say what should be, like, which largest number do you want from the list? So I want the second largest value, so I'm going to put a 2. If I put 1 there, you want the largest value, and we'd get the same result as if we'd done the maximum. They can, if we put 1 here and hit enter, whoops, oh, I got a typo. I got an extra parentheses, but I got 0. They put in an extra parentheses to fix it up. But that's not what I want. I want the second largest. But you can see that was equal to 0 because the maximum and the first largest are the same number. So I'm going to close that up, and then you divide this difference by the range, and here I have the range. And so that's our Q value, is 0.2. And then we have to compare that 0.2 to the value from the table, and then down here we can say yes or no about whether we should reject that piece of data. All right, that's all I have for today. Let your lab instructor know if you have any questions about this.